In this video we will examine the motivation of algebraic identities and why are we learning algebraic identities. We have introduced algebra through a few examples, and you're taking a few examples of where you could use algebraic identities. Because just like numbers, right, if you have a number 2, it's used in so many different contexts because it's not really tied to one item. Same way, algebra can be used in many different ways to find patterns or to prove patterns or to understand things. So we're going to look at 3 things that are interesting. So the first is 2-digit number square. So if the children have been already using something like, let's say 24 square. So they have this method in which they put 16 here and 4 here and 2 times 4, which is 8. And then double of that across here. And this is hopefully how they have been doing their calculation. So if they are using these sort of shortcuts for calculations, then it can be seen that this actually corresponds to using a square plus b square and 2ab. So you can say, okay, 24 is actually, right, so it's actually 2 tens. So I can start using the color. So I can say it's 20 plus 4, where it's in ones, square, and this we know is a square plus b square. So this is equal to, okay, I won't use colors, I'll just use the same color. So it is a square, which is 20 square plus 2 times 20 times 4 plus 4 square. And as it turns out, if this was not 20 and if you had called it x, for example, or a, so you say you have 10x plus y square, so that's 100x square plus 2 times 10 times y, so that's 10 times 2xy plus y square. Now x and y are single digits, so because they are single digits, this will always be a hundreds, which is here, the 400, right? And this will always be a ones, so that's here. So this one's here, this is here, and then you have tens, right? 2xy, which was your 8, and then double 16. 16 gets multiplied by 10, and that's the 10 here. So you can explain that the 2-digit shortcut we are using for squaring numbers is actually coming from here. Okay. Then there is, of course, it's a Vedic mathematics, right? So there's the shortcut in which if you are multiplying 94 with 95, you look at, well, how much is left to become 100? Here it's negative 6. It's 6 short, and here it's 5 short. If you multiply it, you get 30. That's the last 2 digits. And then if you subtract from 94 5, or you subtract 6 from 95, it doesn't matter because it's a cross subtraction, you get 89. In both cases you get 89. So the number is simply 8930. So without doing any major calculations, simply by multiplying 2-digit numbers, you can get a fairly nice result. And if you take another example, it's 90 and 86. So here you are short by 14, here you are short by 10. So you multiply that, that's 140. You actually need the last 2 digits only, so this is a carry. And then of course you subtract this. In this case, this is easier to subtract. You subtract 10 from 86, you get 76. So 76, 1 carry, 40. So 7740. So this is like a very nice shortcut. The question is, how does it work? And if you have the multiplication that you're given x plus a and x plus b, in this case I have written x and y, but this is a and b if you think about it. So you are seeing that this number 90 is 10 less than 100. So it's 100 minus whatever is this quantity, right? And you can make this ab also. Maybe we should. Okay, so we'll make all the x's a's, yeah, and all the y's b's. Okay, so then if we just multiply it out and we do use the expressions that we have, So we have x squared, this one, and then you have the a plus b that you're subtracting, and then you have the ab that's positive. And if you take 100 out, which is the hundreds, right? If you think about the hundreds, so it's this ones, right? These ones. So 100 times what? So 100 times 100 minus a minus b. So this already had minus a, you also remove minus b. This already had b, you remove a. So then 100 minus a minus b, that's the first part of the term, and then you have to add ab to it, the product of the two. So if you see this, you can sort of derive new things, which is what people have done. They have derived new methods that make things look like magic, right? But you can actually explain them. So we have done this and we have done this. Now let's look at square of like numbers that end with 5. So if you look at this, if we take 25 square, then the shortcut is you take this digit 2 and you say 2 times 3, which is 6, and then just 25. So if you have 35 square, you take 3 times 4, which is 12, and then follow it up with 25. So again you have the hundreds and you have the ones, as you can see. So if you take, let's say, 75 square, then we are still saying it is 7 eighths, so that's 56, and then 25. You can directly write these results. So this is neat. Again, how does it work? So if we take the same thing, we say, okay, this is a 2-digit number. So the first digit number is 10, so it's 2 tens. So this is actually 20 plus 5, right? That's what this is, square, right? So if I look at it as this is the digit, so then it is 10 times a plus the second digit b. So 25, this b is always 5. So I'm just going to make this 5. So it's 10a plus 5 whole square. So that is, of course, 100 times a square, yeah, plus you have 2 times ab. So that is, this will become another 10. So that's again 100 times a, right, plus 25. So if you look at it, b square, 5 square, right? So 25. So if I look at this, I can take 100, which is this part common, and I'm getting a square plus a plus 25, which is 100 times a into a plus 1. So this is that 7 times 8, the product of 7 times 8 plus 25. So that's why the 25 is always here. These are always hundreds, so they will never come in the ones and the tens place. So this will always have the 25 and the other thing will shift over. So these are some of the examples of where we can use these algebraic identities. We've used all the identities here. We've used the identity of square in the first one. We've used the identity of square in the last one, right? And we've used the identity of multiplying, let's say, 100 plus a and x plus a, x plus b, that sort of expression. And we have sort of been able to understand how some of these fairly simple but quite powerful techniques work.